All right, good morning, everyone. Today, we're actually just going to work on worksheet 3. The worksheet that you picked up today, worksheet 4, we'll push that to Monday. It's just going to take some time for us to get through the theorems, and we still have to do a little bit more with related rates. So we'll push that off. But I do want to talk about number 3 and talk about something that looks similar to 3. But we go through a completely different process. So just as a recap, this is off of worksheet 3, related rates and theorems. We saw how 3 was a cone problem and realized that with cone problems, as height is changing, radius is also changing. And because of the fact that they're both changing, we have to we can't just replace one with a number because neither of them are static values. So we have to go through similar triangles to create that proportion between the variables so that we can make that substitution. And that just adds an extra step. It just adds an extra step that we have to worry about with cones. So I want to talk about something that looks very similar, but it's a completely different set of process. So on the homework sheet, I want us to do this homework together. This is off of the other handout that you picked up yesterday. This is the related rates and theorems practice worksheet. And I want us to look at number 2. So if we can do that together here. So there's number 2 off of the practice worksheet from yesterday. So let's look at number 2 here. Now, number 2 is talking about a cylindrical tank. So let's draw that shape. Water is being filled at a rate of 3 cubic centimeters per minute. So we know that is referring to volume, but with the rate of volume. So we'll say that's dV/dt. How fast is the height of the water increasing? So we're looking for dH/dt. Now here's the volume formula for cylinders, pi r squared h. And I think something that that students notice is that it looks very similar with the cone formula, right? Basically, it's the cone formula without the pi over 3 in front. But even though the formula looks the same, the process that we have to go through is going to be a lot different and also a lot easier, okay? And this is what I want to point out is as the water level is increasing, as water is filling into the tank, What do you notice about the radius? The height is changing, but what do you notice about the radius? Stays constant. So that makes the process a lot easier. With cones, we can't just replace the radius with a number because it keeps changing, right? But here we can. So because radius is a constant, we can immediately get rid of the radius. We don't have to create a relationship between radius and height. It's a lot easier. But I think the issue that students run into is we've done cones so much that students want to create a similar triangle relationship because we've done that so much, but we don't do it here, okay? Because there's no need to, and also there's no triangles for us to create out of this. So, what radius do we have? 5, and that 5 is going to stay 5 all the way through. So there's actually no need to hold on to our radius variable. We can go ahead and replace r with 5, and that'll just completely make our equation a lot easier to work with. Okay, so we clean this up. V is equal to 5 squared, which is 25 pi h. So we're able to get rid of the radius without having to go through similar triangles. We can just replace the radius that they give us with that value, and then we're ready for our derivative. There's no need to do any involved steps before that. Okay, questions so far? So I'll make sure that even though the equations are very similar, complete different set of process because we have a different, less things to worry about with cylinders. Okay, so now we find the derivative. V becomes dv dt. 25 pi stays. And what does h become? dh dt. Right. How fast is the height of the water increasing? Well, this is easy, right? We just plug 3 in for dv dt, and then we can just divide the 25 pi over, and then we have dh dt. So whenever you see a cylinder problem, you want to just kind of have in your head, okay, this is easier than cones, and I'm going to apply a different process for this problem. All right, so dv dt gets replaced with 3. Okay, divide both sides by 25 pi. Careful though, we do need to keep the pi in the denominator. We can't just move it up. It's going to have to stay in the denominator at the end of the problem. Our units of measure is centimeters per minute. Okay, any questions with 2 from the worksheet? Just wanted to make sure you guys saw that distinction between cones and cylinders. All right. Okay, let's go back to our main sheet and let's look at number 4. So number 4 is related rates for trig. We did this at the near the end of the semester last year. So we did a little trig unit at the end of the semester, and this is one of the topics that we did, related rates involving trig. So let's go through the process, and I want to kind of show you that there's something distinctly different and unique about the way that we approach trig related rates. Okay, but first things first, we're going to gather information. it says in the triangle shown, angle theta is increasing at a constant rate of 2 radians per hour. So what can we assign that 2 radians per hour to?
D theta, dt.
Good, right? We know it's involving theta, but then we have all these contextual words, right? Increasing, you see radians per hour, you know that time is involved. So we're gonna have to make it d theta dt. At what rate is the side length x increasing? Okay, what are we looking for? Good, dx dt. Again, they specify the variable for you, but then they're giving you all this rate of change description. So we know it's dx dt, that's what it's referring to. When x is 4 feet. Okay, so we'll put that down. Now, anytime you see theta with a related rates problem, we know that we have to create a trig equation out of this. Before, right, the equations could be like Pythagorean Theorem, and we saw volume could be the formula, just depending on the problem. But with trig equations, always going to be, or trig problems, always going to be a trig equation. And it's not going to be given to you. We have to create that on our own. But the trig equation is always going to either be sine, cosine, or tangent. So let's look at the diagram here. Theta is kind of like our anchor. That's where we're making our decision from. Which trig equation is, which trig ratio is going to be the one that's most suitable? Sine, right? Because we have opposite information provided. We have information about the hypotenuse provided. So sine is opposite over hypotenuse. So we say sine of theta is equal to opposite over hypotenuse. So we're going to have to create that equation because that is the equation that we're going to be using to find the derivative from. Okay. All right, so we're going to find the derivative, but maybe it'll help if you wanted to push that 1/5 out in front, just to make it easier for power rule. All right, so let's find the derivative. Sine theta becomes?
Cosine theta.
We're dealing with related rates here, so we also need what? Yeah, d theta dt, right? So remember, time is kind of hidden from view, but it's impacting everything that we're doing, okay? All right, what about 1/5 x times dx dt? Yeah, so even though x disappears, we are asking for x's derivative, and because x is no longer the independent variable, it's going to have to be a dependent with respect to time. Okay, questions so far? Okay, so let's take a look at what we have and what information that's given to us and see if they match up. So if you look, d theta dt, right? That's accounted for. We have that value. We know that's where it's going to go. dx dt is what we're ultimately looking for, so it's good that it's showing up for us. But there's something that we have to still work on.
Theta?
Yep, and that cosine theta. But what I want to point out to you guys is that we're not going to worry so much about theta. We're going to worry about cosine of theta. We're going to just have to find a ratio for that cosine theta. I think sometimes I see students get hung up on this problem because they're asking themselves, how in the world am I going to get theta? Okay, so the answer to that is don't worry about theta. Just figure out what cosine of theta is, and they can make a substitution for that entire expression. So how do we get there? So what we're going to do is we're going to create another triangle and see if we can figure out the side length so that we can create a ratio out of that triangle to get what we want for cosine theta. So I'm going to draw another triangle here. And we're going to see if we can fill out the sides for this moment in time. Okay, so what do you think we can fill this out with?
The opposite side would be 4.
Yeah, we know the x value was 4. Okay, this is a moment in time, so we're just taking a snapshot and gathering information about this moment in time. What else do we have?
5.
Okay, 5. So this is enough, right? We should be able to get that third side using
Yeah.
the Pythagorean theorem, right?
Oh.
The Pythagorean theorem, a squared plus b squared equals c squared. But also, I mean, maybe you recognize this as a common 3, 4, 5 triangle. If you can recognize that, you know that missing side is 3, but we can always go through Pythagorean theorem as well. A squared plus 16 equals 25. A squared equals 9 once we subtract 16 from both sides. Okay, take the square root. The negative is not going to make sense, so just A equals 3. So I think we have enough information to make a clean substitution for cosine theta. What's cosine of theta equal to? 3 over 5, right? So we completely bypassed theta. We don't even worry about theta. We're just going to replace the entire cosine theta. Okay, so now everything is accounted for, right? We have something to replace for these 2 missing variables, and now we can solve for dx dt. If I multiply both sides by 5, I can move that 1/5 over to the right side. Uh, 3/5 times 2 times 5, I can multiply that, divide by 5, I get 30 over 5, which is 6. I need to look for my units of measure here. So x is in terms of feet, time unit is hour, so feet per hour. Okay, so I want to make sure that we remember how to handle these very specific problems involving related rates and trig. Right, any questions?
So like, could you also do it like, you have the 4 and the 5, and then you use cosine, and then you find the angle?
You can do that. I would say though that if you see this problem, it's usually part of a non-calculator section.
Oh,
So they would, that's, but.
It's already a Pythagorean.
Right, it's already Pythagorean triple. So I would say that yes, it's possible. Student from previous period, they're solving for theta using arc sine. But yeah, I think they put it as part of non-calculator to see if students understand the concept from this perspective, right? That they're replacing the trig ratio. Okay, let's go to the back, and now we're going to focus our attention on these chapter 3 theorems, like EVT, mean value theorem, Rolle's theorem. So let's look at those. So let's start off with extreme value theorem. I want to start off by just giving you a picture or a visual so that it's just easier to recall. So the whole point of extreme value theorem is trying to find the highest and lowest points on the graph. So the first thing we need to confirm is our function continuous? Okay, if there is a hole or if there's a vertical asymptote, we just have to make sure that they don't conflict with our interval. If they're outside the interval, then we're okay. But we just need to protect whatever interval is given to us. So once we confirm that, and we confirm that it's a continuous function, it does not have to be differentiable, meaning that you can have a sharp turn and still find max and mins, like in this case. Okay, so just have to confirm that there are no holes or asymptotes, but sharp turns are okay. Now, we want to find max and mins on the closed interval, but we want to look for candidates. Okay, and I drew this diagram to help us visualize, where the candidates can be. We can definitely imagine the endpoints being candidates, right? You can imagine the endpoints above or below all the other points on the graph, right? So we have to keep those in mind. But we also are going to have candidates from values in between the endpoints, and those values in between are called critical points, right? These are the peaks and valleys, right? The peaks and valleys of the graph could end up being the highest and lowest points overall for the closed interval. So to find those critical points, we have to work our way down to f prime. And when we find f prime, we're going to set f prime equal to 0. And if there's a denominator of f prime, we're going to set the denominator of f prime equal to 0. And we're going to find each of them separately. Okay. If you set the numerator of f prime equal to 0, you're basically in search of slope zeros. And most of our critical points are probably going to be under the scenario of slope being 0. But we also don't want to forget about the denominator, because the denominator, when we set the denominator of f prime equal to 0, we're purposely seeking out slope undefined, which could be a sharp turn, right? So that's something that we just have to be aware of. Okay, but most of our problems are probably just going to be living in the slope 0 case. Now, after we find our candidates, we're going to want to test them. Oh, and by the way, if we find critical points, are we going to test all critical points? Good. Say it again. Yeah, the ones inside the bounds, right? So there may be an absolute max that's higher than these points, but if they land outside, we don't care, right? We only care about the interval. So it's possible that you find all these critical points and none of them land inside the interval. But I want to make sure that you guys understand that we continue with the theorem. It doesn't fail. It just means that we have less points to test. It just means that if there are no critical points that land inside the interval, then we're only going to test the two endpoints. And we have two points rather than more than that. So we take our valid critical points and our endpoints, and then we plug them into the original function, and then we get their y values. Okay, and then we compare the y values. Your highest y value is your absolute max, and your lowest y value is your absolute min. Okay. All right, so I have those steps highlighted here, but we're just going to jump into number 1 now that I've gone through it from a visual perspective. All right, so find the values of the absolute extrema of the function. We have a polynomial on the closed interval from -2 to 3. State theorem and conditions. Well, we know that the theorem for absolute extrema on the closed interval is extreme value theorem. The condition is continuity. The nice thing is we have a polynomial. It's continuous and smooth everywhere. So we can just, there's no need to do any tests. We know it's going to be true. So our function is continuous from -2 to 3. All right, so we have our endpoints. We know what our endpoints are. We're going to put that to the side because we know at the end we're going to have to consider those as candidates. But now we want to find other candidates. So what's our next step? What do we need to find before we set equal to 0? Yeah, find f prime. Okay, so our critical points is going to come from f prime. So let's find f prime first. All right, power rule. Easy power rule problem here. All right, we set equal to 0, factor, and look for critical points. Multiplies to be -2, adds it to be -1. We set each parentheses equal to 0. So what are my x values? X equals, and x equals 2. All right, we have our potential candidates, and we have to next ask ourselves, are these critical points valid? Can we keep them?
Yes.
Yes, because they both land inside the interval, so we know we have 4 points to test. Okay. So we're going to be testing endpoints with the original function. So let's list them out. F of -2, f of -1, f of 2, and f of 3. Okay, we insert them into the original function, okay, not the derivative, into the original function, because we want to now identify the physical locations of these points. And whatever is the highest, whatever is the largest y value is will be your absolute max. Whatever is your smallest y value is going to be your absolute min. Okay, so I'll speed up the process here. All these will go in the calculator. -2 and for x will produce a y value of -3. -1 into the function will give us a y value of 8. 2 into the function will give me -19. And 3 into the function will give me -8. So what can we conclude? What is my absolute max value?
-1.
But what's the value though? 8. Okay, so we're going to talk about that in a moment. I'll put max next to 8. What's our minimum value? Okay. So I want us to write it this way, because this is an important point I want to bring up. I think many of us are looking at this thinking, well, my ordered pair is my max, right? -1, 8. And my minimum is 2, -19. And I think we sometimes equate the x and the y value as part of absolute max or part of absolute min. But the important thing is that we want to focus our attention on the y value. So we're going to say absolute max value is 8. And then less important is the fact that it's located at -1. And then we can say absolute min value is -19 at x equals 2. And here's the thing I want to point out. Even though it doesn't specify y value is implied. So it says find the values. It doesn't seem very descriptive, but that's how AP exam phrases it. It's referring to the y value. Which means that if this, I've seen this on multiple choice practice problem, where they're asking for absolute max, and they have answer choices of -1 and 8 and two other numbers. And some students are looking at this going, well, there's two correct answers, right? Because -1 and 8 are part of the absolute max, but it's asking for the y value. So without verbally saying y value, the answer is going to be 8. So -1 would not be the correct answer. The answer would be 8. Yes.
So on the AP exam, would they have like an answer choice? Like, let's say this is a multiple choice question. Would they have an answer choice that the absolute max value is -1 and min value is 2, and then another choice that says absolute max value is 8 and value is -19 for min?
I think on the AP exam, it tends to, if it's in this format, they will probably only ask for an absolute maximum or just an absolute minimum. They'll say the absolute maximum value is, and they'll give you all these choices, but you're going to be seeking out the y value of the absolute max.
Okay.
Yeah. I know it's confusing too, because in a textbook, they represent absolute max and absolute max and min as ordered pairs, but you just have to understand College Board AP exam, they're focusing on just the y value. Okay, any questions with EVT? You'll see a couple of practice items of this on the practice worksheet, on the homework worksheet, so it'd be good to practice with those problems as well. Okay, moving on to mean value theorem. Again, I want to start with a visual picture so that we can kind of have some idea before we jump into all these steps. So mean value theorem, okay, is trying to guarantee a specific slope. Okay, that's the whole purpose of mean value theorem. We're trying to guarantee a slope somewhere on the curve. So first thing we have to establish is the function continuous and differentiable on the interval? So that just means no breaks, no holes, no asymptotes, but then also no sharp turns. EVT, it's okay to have sharp turns, but mean value theorem, because our goal is slope related, we got to make sure that every slope exists. So it needs to be differentiable on the open interval. If the sharp turn is outside the interval, then that's fine. But as long as our open interval is safe and protected, we can move forward. So here's what mean value theorem, what we would do. You would take the endpoints that they give you, and then you would find those ordered pairs with the original function. And then you would use a slope formula to find the slope between the endpoints. And then when you find the slope between the endpoints, that is going to be what you're trying to guarantee. So let's say the slope between the endpoints is 1/2. Then I know that somewhere along this path, there's going to be an exact slope of 1/2, at least once, right? Maybe more than once, but at least once. So what we're going to do is we're going to find the location where that particular slope occurs. Okay. So what we're going to do is we're going to find the slope between the endpoints. We're going to find the derivative, and we're going to set them equal to each other. And when we set them equal to each other, we can find the location where that slope occurs. But you're going to see in this problem, they're going to imply mean value theorem without actually stating mean value theorem. And the way that they're going to say it is, they're going to ask, when is the instantaneous rate of change equal to the average rate of change? Whenever we see that description, we have to just internalize that as, okay, that's referring to mean value theorem. And I'm going to apply mean value theorem steps. Okay, so let's look at example 2 here. It says, I just want to give another quick example here. This is just a visualization or an example. Let's say you're taking a road trip, right? And that road trip was 300 miles. And it took you 5 hours to complete that road trip. And you're trying to figure out, okay, what's my average speed? The average speed is just distance divided by time. So 300 divided by 5 would be 60, right? So your average speed is 60 miles per hour. So the question is, can you guarantee that somewhere along your trip that your speedometer reached exactly 60 miles per hour? Yes, right? Doesn't mean that you're spending your entire time driving 60 miles per hour. Maybe most of your time is below and then the other half is above, but you can't have an average speed of 60 miles per hour without actually reaching 60 miles per hour at least once somewhere along that trip, right? So that's what mean value theorem is doing, is once we can gather that average slope, we know that slope must exist somewhere between, or that rate of change must exist somewhere between. And then we're looking basically for that specific case. Okay, so let's look at example 2. Oh, I do want to point out, these are the steps we're going to take though, okay? Very specifically, we're going to take the x values that they give us, we're going to find the order pair, and our first goal is to try to get the slope between the endpoints. We're not going to worry about the derivative. We're going to spend all of our efforts in the beginning trying to get that slope, trying to get that order pair. So no calculus in the beginning. Let's get that target slope value first, and then we'll turn around and figure out the derivative, and then we can set them equal to each other. Okay, so we have a function x plus natural log of x. What is the value of c for which the instantaneous rate of change is the same as the average rate of change? So we see that description here. It doesn't say mean value theorem everywhere, but they are clearly describing mean value theorem. So first things first, we need to identify order pairs so that we can find the slope, because we're going to target this side of the formula first. Okay, they only give us the x values, so we're going to spend time to find the y values. So I'll find f of 1, I'll find f of 4. So put into the original function 1 plus natural log of 1, 1 plus 0, which is just 1. Okay, we put 4 into the function, 4 plus natural log of 4. Use your calculator. It's going to give us 5.386. So our next step is to find the slope, right? So just do change in y over change in x. Clean this up, we get slope is equal to
1.46.
Yeah, 1.462. All right, so we have that target slope identified. Now we can move on to find the derivative. Okay, so let's find f prime now. All right, what is x going to turn into? 1. Natural log of x turns into 1 over x. So we have our slope formula. We have the slope that we're targeting. And we're just going to set them equal to each other. Or another way of thinking about it is I'm going to replace the slope slot with a specific slope value, and I'm going to solve for x. When I solve for x, I can figure out the exact location where that exact slope of 1.462 sits on the curve. Now, this is an equation that we can solve by hand. This is not a difficult equation to do. But I do want to make this into a calculator question, because I do want to point out sometimes you're going to have problems where you're forced to have to use your calculator to find a solution, because algebraically you're just either there's no way to factor, and you have too many x's, and you're going to have to look for an approximation. So we're going to practice the calculator steps, even though this particular problem doesn't necessarily require a calculator. But I want to kind of have us practice that. So when you have a messy equation to solve, what you want to do is you want to set your equation equal to 0. And I'll show you on both calculators how we can solve a seemingly messy equation. So we're going to do that here. Let's set it equal to 0. So I'm going to bring everything over to one side and then have 0 show up on the other side. Combine like terms there. So now what we're going to do is I'll do the graphing calculator first. We're going to put 0.462 plus 1 over x into the equation, and we're just going to look for the x-intercept. So go to y equals 0.462, sorry, plus 1 over x. I'm sorry. It was 1 over x, it should be minus, right? My bad. Yeah, I need to change those signs there. Okay, yeah, so it should be 0.462 minus 1 over x. I'm subtracting that 1 over x over. All right, so let's graph this. So do zoom 6 to get to your standard window. And it's tough to see, but it looks like it's going to be living somewhere in this region. And also the nice thing about multiple choice is you kind of have an idea where those numbers are going to be, right? You know it's going to be somewhere between 0 and 3. So I'm going to just zero in on that region and just give myself, create a box using zoom and just see if I can get a closer picture of that region. Hit enter. Okay, so we're going to look for that x-intercept. So to look for that x-intercept, you do second trace and 0. So second trace 0. From here, left bound, so you can choose a point on the left side of the x-intercept, hit enter. Right bound, you're going to choose a point on the other side of the x-intercept, hit enter. And now the calculator is going to look between those two endpoints, and we're going to get x is equal to 2.164. Questions with that method? Some students also mentioned the fact that there's a solver application on the 84. So if you go to math and go to the very last option, math solver, you can do the same thing as a num solve on a 36 Pro. You can set the equations equal to each other and solve for x. It's just that it's not as visual with the solver, and so if you have multiple x-intercepts, it's only going to find one, or you may not know exactly how many there are. But having a graph in front of you, you can convince yourself, okay, there's only one, or you can get a more visual experience rather than using solver, which is fine. But also, I know that some calculators don't have the solver, so that's why I like to show that graphing method. Okay, so you would just set the equation equal to each other. You would pick a value that's a number that you can start with, and then it'll look for that that solution for you. Now, if you have the 36 Pro, you would go to num solve, and you would do the same thing. It's just that you don't have the benefit of seeing the graph, so you just have to rely on the equation here. So you say 0.462 minus 1 over x equals 0. Hit enter. And I like to start at 1. I think sometimes students start at 0, which is fine. It's just that sometimes 0 gives an error because the equation has a 0 in the denominator for the x. So, or x in the denominator. So 0 is going to give an issue. So if I use 1, then I'm usually going to be pretty safe as a starting point. Hit enter. (2.164), same thing. So we have a location on the graph where a slope of 0.462 or 1.462 is reached. And is this going to be safe inside my interval? It should be, yeah. So we're always guaranteed at least one solution, but we're just double checking. Yeah, so C equals 2.164 on the open interval from 1 to 4. Sometimes you may have multiple C values, which is fine. Just make sure that all of them fall inside the interval. Right? Sometimes you may have a value that's outside the interval that you don't want to keep. Okay, any questions with mean value theorem? Okay, one more thing, Rolle's theorem. Rolle's theorem is a very specific case of mean value theorem. But mean value theorem is more general. Mean value theorem just says, okay, whatever the endpoints are, just find me the slope. And I'm going to locate where that slope that I find between the endpoints. But Rolle's theorem is very specific. Rolle's theorem is saying, I'm trying to guarantee a slope, but it has to be a slope 0. I'm looking for a slope 0. So in order to guarantee a slope 0, I first have to, again, involve the endpoints. I'm still going to find the order pairs at the endpoints, but now my endpoints is very restricted. I need the endpoints to be exactly the same value, because if the endpoints give me the same y value, that means I can draw a horizontal line between them, which means it's a slope 0. And if I can get a slope 0 between the endpoints, then I can therefore find that location where a slope 0 is guaranteed to exist somewhere along that curve. Okay. So it's pretty similar with the mean value theorem formula. It's just that if we can verify that f of a and f of b are equal, then we know that this right side is always going to be equal to 0. So it's kind of like a simplified version of mean value theorem, but also a very specific case of mean value theorem. So let's look at Rolle's theorem. Number 3. Let f be the function x cubed minus 9x plus 1. Find all numbers c that satisfies the conclusion such that of Rolle's theorem such that f prime of c is equal to 0 on the closed interval from 0 to 3. So we know that our function is continuous and differentiable. We're good there. Let's just go ahead and write those down. All right, polynomial, no issues with anything slope related. So we have to worry about the endpoints, right? The endpoints have to be very specifically the same. Otherwise, Rolle's theorem doesn't apply. I mean, mean value theorem will still apply, but just not Rolle's theorem. So we take our endpoints, put it into the original function, and see if they give us the same locations. All right, so f of 0 into the original function, I get 0 minus 0 plus 1, which is just 1. And if I put 3 into the function, (27 minus 27 plus 1). So does Rolle's theorem apply? Yes, because my endpoints are nicely located right across from each other. So now that we've confirmed f of a equals f of b, we can then set f prime equal to 0. Because now I know that somewhere along the graph, I'm guaranteed to get a slope 0 on the curve. A common mistake that I see that students make is they would find f prime, but then they would set f prime equal to the y values. But that's not what we're trying to do, right? We're trying to, because these y values are the same, we know the slope is 0, right? So we don't want to set it equal to the ordered pair. We want to set it equal to the result of those ordered pairs, which is a slope 0. Okay, so f prime. Set f prime equal to 0. So now we're trying to find a location where that slope 0 occurs. Add 9 to both sides. Divide both sides by 3. How can we get to x? Square root, what's going to happen with square root? Plus or minus. Okay, so we have two potential solutions, two potential places where there's a slope 0. But what do we have to consider? The bounds, right? So even though there may be a slope 0 in both locations, for our problem, though, we only care about our interval. So anything outside the interval, we're just not going to keep. So our interval is from 0 to 3. So negatives is going to be out. Just c equals root 3. Okay, any questions? All right, we didn't get the chance to get to worksheet 4, so we're going to do worksheet 4 on Monday. So I'm going to be pushing the assignment due date to Tuesday. So right now, I updated assignments 1 and 2 on Teams to reflect that it's due on Tuesday. I'm going to be pushing out assignments 3 and 4 on Teams later this afternoon, and that's also going to have the same due date, Tuesday night, midnight. And I'll send out a reminder this afternoon as well. Okay. Also, I'll send out a reminder that anyone who wants to do the recovery test for chapters 5 and 6, send me an email or send me a remind. And then your assignment for your recovery is due Sunday night. But I'll send out a reminder for that. But yeah, that's all I have. Hope you guys have a great weekend. See you Monday.